Okay, is it live? Okay. Hello, everyone. I'm José Roberto, not Mateus, as the name says. I am going to make a presentation, kind of journal club style, just about a paper I was reading. The paper is, as the name of the presentation says, Detecting Ultralight Bosonic Dark Matter via Absorption in Superconductors. So, well, first rule for this presentation is there is a lot of information onto solid state physics, and well, I'm not that familiar with solid state physics, so let's not let's not get very much into that, please. So the idea is that, okay, the paper, let me give a brief review and a brief overall of the paper. The paper goes on to ultralight dark matter. Ultralight dark matter is like sub GeV, and actually it's just like MEV, EV, and sometimes KEV dark matter. But mostly here, she and they go on of order MEV dark matter. Okay, I think this says milli 10 to the minus 3, right? So okay, well, the starts giving us a brief review on dark matter, stating that, well, we don't know very much about it, well, other than there is dark matter. So okay, and we have had several searches for dark matter: xenon again, panda again, several corporations, several people looking for dark matter, mostly winged dark matter, because that was the main paradigm, solved the problem. But well, we haven't seen it, so we have to look for other possibilities, and they propose using superconductors. All right. So how do they propose it? So it's very quick presentation because it's just an overview. Well, the main proposition also, okay, I think everyone knows what the superconductor is. One that has basically no resistivity, right? Okay, so the conductor with no resistivity. Well, the proposition is, okay, so it will happen. We will be able to detect directly detect dark matter by absorbing the bosonic dark matter. An electron will absorb the bosonic dark matter. And here the paper treats for 3 types of bosonic dark matter: the dark photon, the pseudoscalar, and the scalar, right? And then the electron absorbs it and emits a phonon, right? A phonon is a vibration mode on the crystalline structure of the thing, right? So, okay, these are the 2 relevant Feynman diagrams at 3 level that we have. So basically what happens is a bosonic dark matter comes in with momenta Q and momentum Q, the electron momentum K, and then we get like a phonon with momenta Q, capital Q. Well, okay, so the basic idea, so the paper goes around a little bit about momentum conservation on the lattice, because we have a few caveats here from, okay, again, solid state physics, that we have in situ, I think how to say it, each square in the lattice conserves momentum separately. So it goes about that. And it says that the only way to solve the problems is if we have actual phonon emissions, and what we detect is the phonon emission, which is the vibration. The phonon emitter here has a lifetime long enough for us to detect. So saying that the phonon has a lifetime. Okay. Well, this is just momentum conservation in the lattice. And then they used the Debye model for the phonon, which says that basically the dispersion relation for the phonon obeys this. This is the speed of sound in the media. This is the moduli of the 3 momentum. And this is basically, well, the energy because of this relation here, right?
Q is the phonon.
No, the phonon is capital phi here. Capital Q is the momentum of the phonon. Yes. All right. Well, that's basically it for the idea. We will be able to absorb dark matter and detect it by the emission of a phonon. It has a specific signal, and that's basically it. So it goes around a little bit. So it says that they will use mainly aluminum for it. So they give us a little bit of relation. So omega here is the maximum frequency for phonons in the media, and they give us the ratio of the maximum frequency and of the speed of sound, which is over other KeV. Good. All right, so we go around a little bit about dark matter absorption, just the basics of it. It's just like the usual direct detection stuff. The rate per unit target mass per unit time, this is just the absorption rate, goes with the 1 over rho of the material and the ratio of the mass density of dark matter and the dark matter mass. And then we have the averaged thermally average cross-section here, in which this is the number density for electrons, which is the target, this the cross-section for absorption, and the relative velocity in the lab frame for dark matter and electrons. Okay. All right. So the absorption cross-section is calculated. So the thermally averaged absorption cross-section will be calculated as usual. We have here the integral in our space. Basically, the averaged amplitude matrix squared. Yeah, I think that's how you say it. And then you have several things that come from the Lorentz invariant phase space. And these guys here are the distribution functions for the electron. If I'm not, yeah, that's it. We have the distribution function for the electron that was there. And then we have the Pauli blocking that appears here because, well, we know that particles with half integer spin cannot occupy the same energy level. So you have this Pauli blocking here that is relevant. But again, the paper says this is okay, but they do this approximation here for using the half-side theta function in this regime in which the particle momentum, tree momentum, is smaller than its energy, which is smaller than the Fermi energy of the material. Okay, then they do this for 0 temperature. It's in Kelvin, so everyone's okay. All right, so they do this approximation here. But what they basically say is that they will not solve this until they use the scalar problem. Okay. Well, okay. So they give a little bit about how phonons couple to things. They use this phonon coupling here, which I don't quite understand how it comes. I would have to read. This reference is a book, Kitto, for solid state physics. Yeah, that's I have never read it, so that's why I don't know it. No, Kitto is solid state physics, but you have to solve it in the lattice. So I have never solved anything in lattices so far. I'm reading another book, not Kitto. People said Kitto is not that good for it, but okay. All right, so this is the coupling for phonons. It's the dimensionalist coupling they use. It's just they're just stating they are how do I say it? Conventions. They're just stating their conventions for the coupling of the phonon. All right. That's it for here. And then again, they will then, so their idea is the following. Well, we have to use things that we have, right? To at least get a sense of the sensitivity, what we have. And what we know for aluminum, for instance, is the absorption spectrum for photons. So what they would do in this paper is that they will compare the rate of absorption of our dark matter particles with the absorption of photons. So they will solve the Feynman rules and stuff, and then they will compare with photons. That's why they state over there, this is the amplitude matrix squared for photon absorption in the medium, okay? And it relates to the tau here, which is the time scale for the phonon emission, okay, not the phonon relaxation time. So the phonon emission. Well, then it goes a little bit about, again, this is the solid state part that I said that I am not entirely familiar with, that they use, well, I asked a lot of people yesterday about this, the optical theorem to relate the rate of absorption of photons with the imaginary part of the polarization tensor of the medium. Okay, so well, that's something I'm not entirely familiar with. So I'm sorry if I do not make myself very clear here. But
it would be like the transition amplitude.
Not the transition amplitude, because this is the.
But this,
Yeah. Yeah.
So if you decide is the cross section,
Yeah,
the sign has to be the amplitude.
I'm not entirely sure because this is just polarization. So it's just how the it makes physical, it has physical reasoning because it's how the medium responds
Yeah.
to a photon in it. But the mathematical behind it, I'm not entirely sure.
Yeah.
But okay, you can see like, so the optical theorem relates Green's functions to matrix amplitudes. Basically says that the amplitude you have for all the processes going, it relates to the imaginary part of the Green function, and the Green function relates to the polarization as well. You can write it in terms of the polarization. Well, okay, I'm not gonna go very into this. So they say that the polarization, I have to go to the appendix here. Let's go. Oh, where is it? Here. So the polarization tensor, this is the tensor, okay, has transversal and longitudinal parts. Okay, the transversal, again, 1, 2 would be if you want to x and y, and then you have longitudinal and z. And they basically say that for a certain regime in which the dark matter particles' tree momenta is very much smaller than its energy, basically say it's non-relativistic, you would have that these two weights here for the polarizations are the same. That this is an approximation they make. Let's go again to where I was. Where is it? Here. Okay, good. And then they use this result in which you relate the polarization with the complex conductivity. You see this imaginary part here, and then when you multiply it by, this is the complex conductivity here. And then you get the imaginary part of it, which will basically be sigma 1 for us here, all right? Because you multiply by I, and then you get this I off, and then you only have this I here, okay? Well, all right. So basically what you say is that the sigma 1 is the quantity we want. It's the quantity we want to have from experiments to compare with the results we want to get. They use the Drude model for the theoretical development for the sigma. The Drude model has this result. Why? I'm not entirely sure. Okay, the Drude theory gives this. And again, tau is the same thing. And they do this for an approximation in which sigma 1 will be equal to this omega p squared, which is related to, let me see where they define it. I think they define it. Here, omega p is this for aluminum, 12.2 electron volts. They do it in the limit where omega tau is greater than 1. All right, they do this. And okay, omega p here defined again. Just this ratio here, square root of this ratio. Why is this the mass of the electron with a star on top? Because it's the mass, the effective mass of the electron in the material. It's electron interacts with the material, so the measured mass, the measured pole of the Green's function will be different. Right? We have the spectral theorem, so the measured pole of the Green's function will be a little bit different than for the free electron. All right, so we have here, so this is just theoretical development. This is the rate for the electron to emit the phonon in the media. It relates to this lambda, a few constants we have for the material, this lambda here, this omega d, and its frequency or energy, in our case, dependent. Okay, so they do for Drude theory. And then we have this, which is what we want. It's related to absorptive part of conductivity in low temperature aluminum. They do this for energy below 0.2 electron volts. You see here, this is the graph here. This is a they show this for up to 10 to the 1 electron volt, but they do an interpolation using approximating for omega to the -3 here. So they will use this to do the comparison with our theory. Okay. Basically just doing, well, this is related to the material itself. It's not important to the physics that I want to discuss here right now. All right. So as I said, they will do it for dark photons, pseudoscalars, and scalars. Dark photons, first of all, they do it for Stuckel bag mass, which makes the phenomenology different from breaking symmetry, because we do not have a dark Higgs here. Okay, so we only have simply a dark photon, massive dark photon. This is where the dark photon comes from. I think you guys remember Lucia's presentation of the dark photon. You have this guy, and then you do the rotation, and you get you diagonalize this term, and you only get like a dark photon if you give them mass. There you go. This is the rotation. If you give them mass, you have that the electromagnetic current gets a dark charge, as they say here, which is just the electric charge multiplied by the mixing angle, right? And we want to find bounds on the mixing angle, which is also here. This kappa here is the mixing angle between the dark photon and the photon. You can also understand by looking at, if you want, I can draw here a final diagram later. Well, okay, so you can find that these not when you calculate the absorption rate of the dark photon in the media, kappa is not just kappa, but it's a kappa effective, because the same way the photon behaves differently in a media, dark photon will behave differently in the same media. This kappa effective, again, is related to the polarization tensor, as we would have expected from physical reasoning, and relates to the real part and the imaginary part. And then they use a approximation here, in which the real part is just omega sigma 2, and well, the imaginary part omega sigma 1, which is just saying that the dark photon also has a dependency on sigma 2, despite what we would have expected. Okay, so what they do then is basically find how the amplitude matrix relates to the photon amplitude matrix, which is basically just with the kappa effective in the front, which is what we usually have for the dark photon. And then they find the rate. They also use, I forgot the name for it, in which the frequency of the photon equals the mass of the dark photon. There is a technical name for this, but I don't remember right now. This is one thing they state. And then you find this thing here. I think it's for 3.5 sigma it's 95%, yeah, 3.6 sigma. No, sorry, 95% confidence level with 3.6 events from 1 MeV to 1 eV, and they have a background of very few solar neutrinos in this regime here, from 1 MeV to 1 me. I don't know how to say this, to 1 electron volt, and then they in the electron volt to 10 electron volt, because the absorption signal will be monoenergetic, they neglect the background. While neglecting the background, they find this sensitivity here. Okay, so these two here, shaded one, is similar to what Lucia showed in her presentation, as just what we have for bounds right now: stellar constraints, emission, and the xenon 10. This is, in our case, for Stuckel bag, and they also stay here for horizontal branch stars, in which case we have the Higgs. Okay, when we have the dark Higgs, it's a little bit different. As I said, the phenomenology will behave differently. And what we have here is in the bold black curve is the expected sensitivity for an aluminum superconductor detector in exposure of 1 kilogram year. And this thin line here is for 1 kilogram day, which basically says that the expected sensitivity for this proposed detector is greater than what we have for current bounds. Okay. All right. The other, okay, I think everyone's okay with the dark photon. Is everyone okay with the dark photon? I think so. Okay. Yes, everyone is. No one has anything. All right. The other model they consider is the pseudoscalar. Well, they use this specific coupling here with the derivative. All right. This A here is the pseudoscalar. It could be the axion-like particle. Okay, the axion-like particle. And then they compare again the amplitude matrix with the photon amplitude matrix you see here. And what we find is bounds on this coupling here, which is the coupling between the axion-like particle and the electrons. Hi.
Just that you said the kinematical axion coupling is always like this, because the axion would have a relationship with the Higgs that derives from the Yukawa interaction, and the interaction between the axion or axion-like particles to ferment, they usually are
like this, right? With the derivative, you say? Yeah, okay. Thank you. All right. Where was I? I was here. Okay, so this is the amplitude matrix square. With the amplitude matrix square, you can find the rate again by comparing. Again, you see that the sigma 1 is what we always want, which is what we have measured from the experiments. All right, so from this bound. Okay, so something they point out is that if the axion only couple, axion like the pseudoscalar, let's say like this, only couples to electrons, you find this loop-induced photon coupling with the pseudoscalar, which is somehow very also important here. And you can find other bounds from it, which they plot as well in here. You see the axion, the pseudoscalar going to photon. This is a current bound from experiments they have. But this is if the only coupling to leptons is with the electron. If not, they have an order 1 correction, if I'm not mistaken. They say in the paper. All right, so these are current bounds on the shaded regions. We have the QCD axion from white dwarfs, emissions in white dwarfs, 0 100, cast, and horizontal branched stars. And the expected sensitivity, again, the same thing. Bold is 1 kilogram year, and thin line is with 1 kilogram day. You see that QCD axion has some kind of overlap here, and the expected sensitivity is up to 10 to the minus 12 on the coupling, right? Again, the x-axis is also in the mass range. The last one they do is for the scalar one. You have this time is just usual Yukawa coupling, if I'm not mistaken in the name. Okay. And again, but in this case here, it's a little bit different. They do solve that equation on top. They say they do, at least, right? This equation here for the specific thermally average cross section. Okay, let me go there again. No, okay, so they do it and they find the rate, and we have two regimes here where omega is smaller than that omega d. I defined that, and omega is greater than omega d. Right? There's a small difference here, small, no, very relevant difference. And again, what's important for us is the plot, which is here, and we do have a region for the coupling, which has not been yet covered by current bounds for the 1 kilogram year exposure for scalar dark matter, usual scalar dark matter, which is in the around 10 to the 7, 10 to the 6. Right? You can, again, emission, they usually come from boson, come from like emissions in horizontal range stars. Well, I think what I got from this paper is that the dark photon, as usual, is the one that we have a greater sensitivity and the good one. Well, that's basically the paper, I think. Do you guys have any question, please? No? Okay, thank you.
Do you know if there's any relation to the crest experiment?
With this guy, I'm not familiar.
The crest is also a superconductor.
Probably has. I'm not familiar.
But it's 2016, so maybe.
Yeah, it's old. It's an old paper. It's from, oh no, it's 2016, but it's not very recent.
Remember that crest is also superconductor, and I asked him about the cross section with the optical theory. Let me see, he has answered.
Okay, well, you can talk to me later about it. Does anyone have any other questions? No? Okay, that's it. I think I hope I have made myself at least a little bit clear. Thank you.
Ele disse que é só multiplicar por todas as polarizações possíveis.